Hey everyone, so today we're going to quickly go over how to use math notation. So let's just get right into it. I'm only going to cover these four today, mostly because they're extremely common in math papers, and I think they're the ones that are also pretty easy to understand. So let's just get right into it. Now, I've already written out pretty much everything you need to know, and so we can just get right into it. The first one is going to be the element of. So this is represented by the epsilon symbol. And you see here that I've written some things. So imagine that this is a number line and it's the real numbers. So this of course represents all real numbers, and consider that you only think about the ticks. Well, if you only consider the ticks, you know that all the ticks are still on the number line. Yeah, we're not thinking about the numbers between here like the rational numbers, but we're still thinking about numbers that are part of the real numbers. In fact, each of these ticks represent an integer, and so we say that the integers are an element of the reals because they are on the number line. Look at it, right? Another example here that gets more specific is you can apply this to anything. 2 is an element of 0 and 4. Pi is an element of 0 to 6 because they're on these intervals. A way to think about it is if you have the big overarching space of real numbers, whatever else is in this box, like the integers, the rationals, the natural numbers, pi, e, root 2, these are all subsets. All the blue things, they're part of the bigger whole. That's what this is saying. For the next symbol we're going to talk about, which is for all, which happens to be part of the channel logo. For all x in reals is a good example to understand this. So for all means for any value of something. So when I say for all x in reals, I mean that for any value of x. And of course, that's an incomplete sentence. So here's an example. Let's say that I want to say the function f is increasing on the interval from 0 to 1. Assume it's continuous and differentiable. Twice differentiable, in fact. The way to write this is, now there's no actually way to say f is increasing without using words. So instead we say f prime of x is greater than 0 because that means that the function f is increasing, but we want to specify when it's increasing because it's on 0 to 1. So we say that this is true for all x values in 0 to 1. This sentence is incorrect if you don't have the for all x. But with this, we can now say for every single x value on this interval, the derivative of f is positive, which means that for every single value of x, the function is increasing. Notice that now we begin to use a combination of the things we learned. So the epsilon symbol is back here. We also have the for all. And note that when we say on an interval from 0 to 1, we mean that x is between 0 to 1, inclusive if it's brackets, but in this case, it's parentheses, so it's not inclusive. For this symbol, there exists, it's a backwards e. If f, and a good example here is the mean value theorem from calculus, which says that if f is a continuous and differentiable function on the interval from a to b inclusive, then there exists a c for which the derivative at c is equal to the average rate of change of the function f on a to b. So notice instead of saying there exists, we can simply write this, and that will tell us that there is some value for c for which this condition is true if these conditions are met. So there's how to write the mean value theorem. And of course, we can be even more specific here and say that a, b, c are all real numbers. So that's another way to add even more. We could even add a for all a, b, and c that are in real numbers, and this would be an even more specific definition, although I think that's going a little bit too far. And lastly, for these subsets, if we want to write things as going into set theory, just like this symbol or this notation up here, we can actually write that the same way as saying that the integers are simply a subset of the reals. This applies more to some other topics like linear algebra, vector calculus, probability theory, measure theory, and all that sort of stuff. Because let's say, I want to say, there is an ordered pair or ordered triple of the following form, a comma 0 comma 0, for all a that are real numbers. Well, you can say that this is a subset of the vector space, and this is true because you would prove that this is non-empty, and then you would prove it for closure under scalar multiplication and addition. I'm not going to do the proof there. That's a little bit too much work for me. But the idea here is that we are allowed to say that this set of ordered pairs for any a value is a subset of a vector space because it satisfies the same conditions as a vector space. In fact, this idea is more present in this kind of stuff where we're dealing with sets and subsets, so set theory, rather than individual elements, right? 2 is an element of 0 and 4, not exactly a subset. Although you can make that argument that 2 indeed is a subset, but really it isn't. Although that's up to debate. I don't know, actually. Well, there you guys have it. So this is how you actually write math notation. This is a very basic introduction. And so we're going to go over more of these as we go and make more videos. But this is the first 4. And also on the screen, you're going to see some research papers where this is very prominent, as you see on the screen right now. And so definitely understand that, yes, this is one of the things that are very applicable and useful for you to understand what's going on. I hope that this has been very helpful to you in your math journey. Thank you for watching. Subscribe and like if you enjoyed and if you want to watch more content. See you guys later.